Luckily for us, some of the other variables are easier to handle. Pressure is a piece of cake. Pressure, if you increase pressure, it'll always shift to the side with less moles of gas. Okay? So what you need to do is you just look at the, now if you decrease pressure, it'll shift to the side with more moles of gas. And all you really need to do here is literally count the moles of gas on the two sides. So for example, if I were to increase the pressure in the first one, I literally can count the moles of gas. So I've got 1, 2, 3, 4. See the 1 here and the 3 here? I literally add them together, but I make sure I look at what's in the parentheses. So there's 4 moles of gas on the left, and there's 2 moles of gas on the right. So if I increase pressure, it will shift to the right. And that will cause the amount of NH3 to go up and the amount of these two gases to go down. Essentially, it will basically decrease the pressure because there'll be less molecules. Because for every 4 molecules of gas consumed, you get 2 molecules of gas made. So the actual molecules banging against the walls of the container will decrease. So when you increase the pressure, it will relieve the stress by decreasing the pressure. Now, make sure you're clear. If I were to decrease the pressure, okay, it would have the other effect. It would go to the side with more moles of gas. Make sure you count and also remember, if you decrease the volume of a container, it's the same as increasing the pressure, right? Because for gases, when you make the volume smaller, the pressure goes up. That doesn't show up much, but you might want to be aware of that. Okay, that indirect relationship we talked about Boyle's law earlier in the year. Now, 1 and 1, and you see the 2 over here. There's 2 moles of gas on the left in this one and 2 moles on the right, which means the number of moles of gases on both sides are the same. So in spite of the fact that there's gases in this equation, changing the pressure will have absolutely no effect because the number of moles of gases on the two sides is the same. This is the one that's sort of tricky for a lot of students. And the reason why it's tricky is because it's the same thing on both sides. But they love this on the Regents because it's something everybody sees. This is what happens in a bottle of seltzer. This happens in soda. Soda is carbonated water. It's not like carbon's in there. Carbon dioxide's in there. And when you have a bottle of soda, there's carbon dioxide dissolved, and there's the bubbles, and that's the gas. Now be careful because on this side there is 1 mole of gas. But on this side there's 0 moles of gas. Because when the CO2 dissolves, it behaves like a liquid, not like a gas. So in this particular case, if you were to increase the pressure, it will shift to the side with less moles of gas. It will go this way. Now this is consistent with what you learned earlier in the year. When you increase the pressure on a gas, it becomes more soluble. That was in the last unit. It was part of the test. It showed up there, right? This is why. When you increase the pressure on a gas, it shifts to the side with less moles of gas, the AQ side. If you decrease pressure, it shifts to the other side. And this is why when you uncap the thingy, most students get confused. When you're uncapping the thing, you're lowering the pressure, okay? The pressure in that thing when it was capped was really high. You open the thing, the pressure is now the same as it is in the atmosphere and everywhere else. That's less pressure. It shifts to the side with more moles of gas, and all of a sudden you see bubbles, lots of them. Okay, be careful. I'm not going to go through the last example, but there's 0 here, 0 here, and 1 mole of gas over here. So it's going to be the same thing. Okay, if you increase pressure, less moles of gas on this side, shifts that way. All right, the last variable is temperature. I'm sorry this video is so long. I'll try to make them short, but Le Chatlier is a tough concept, quite honestly. For temperature, you need to remember one statement. If you want to repeat after me, no one will hear you. Do it. An increase in temperature, okay, favors the endothermic reaction. So when you increase the temperature, it will favor the endothermic reaction. If you lower it, it'll favor the exothermic. Now, this is the one thing that can actually affect the equilibrium constant. All those other shifts actually end up leading to the same value for the equilibrium constant, which I'm not going to really get into, but this one will actually change it. So that's why they always give a temperature whenever they give an equilibrium constant problem, to indicate that this is what it is at this particular temperature. Now, you have to be really careful. What I usually tell students to do, okay, is to look for either heat or look for a delta H and then label the 2 arrows. See how the heat's on the right in the first equation? That means this way is exothermic and the reverse way is endo. Once I've done that, it's a piece of cake, as long as I remember this one thing. Okay, an increased temperature favors the endothermic reaction. See the delta H is plus 20? That means that the forward reaction is endothermic in this case, okay, and the reverse one is exothermic. Once you have it labeled, it's pretty easy to do. Now you're like, oh, well, I increased the temperature. Well, for the top reaction, it's going to shift to the right. I'm sorry, I messed up. Oops. We're going to erase that, and we're going to forget what I just said. When you increase temperature, it will favor the endothermic reaction. So for the top one, it will shift to the left, because the endothermic is this direction, which means the amount of A will go up and the amount of B will go down. So, and this also tells you how the equilibrium constant is going to change. If it's going to shift to the left, then you have less product and more reactant. So the value of K, since K is products over reactant, will actually decrease. For the bottom one, if you increase the temperature, it will shift to the right. And so if you increase temperature for the bottom one, the value of K will actually increase because you'll end up with more of D and less of C. Look for ways to tell which way is endothermic and exothermic when you're doing them, because if you don't look for those cues, you're going to have a tough time. There is a trick I'm going to mention. I know this video is long, but I'm going to throw in the trick at the last second here, which is this. You can look at it this way. Some students are very visual about this, so I'm going to just do it like it's very visual, okay? If you look at the reaction, I'm going to erase all this other stuff on here, okay? So let's say, if you were to add B, if you understood what we did so far, then you ought to know that by now, if I add B, it will shift away from it to the left. If you increase temperature, if you see heat in the equation, you can treat it almost like it's a reactant. It's very visual. If you increase B, it will shift away. If you increase temperature, it's like you're increasing heat, it will shift away from it. So if you can find the heat side of the equation, like if heat is over here, and you've got like, plus C, arrow, D like that, if you increase the temperature, it will shift away from the heat. Okay, because that will be the endothermic way. Okay? So whichever way, if you're going away from the heat, that's the endothermic process. Okay? And if you lower the temperature, it will shift towards the heat. Okay, so that's a really easy way of doing. I'll repeat that one time just so you get. If you increase the temperature, it will favor the endothermic, and that direction is away from the heat. If you decrease the temperature, it will shift towards the heat in the equation, because that way will be the exothermic. This is the endothermic direction, and this is the exo. All right, those are the three things. There's some handouts to do based upon this. I hope this helps.